All right, so here we go. This is today is what is it? May 13th, and so in case you're gone from class today, this is our demonstrations on force vibration. How can we make a tuning fork sound louder? There's two ways that we can do it. One way is to hit it harder. And the other way that Jade can attest to is move closer. And again, that's because sound is an inverse square law. A third way, and the one that usually people do not realize, is that you can force something else into vibration. So another object may be forced into vibration by making contact with, in this case, that tuning fork. What that does is it increases the amount of matter or mass that's vibrating. So the tuning fork itself doesn't have a lot of mass. It's just a single set of tines going back and forth. When I take the table and get it to vibrate along with it, I increase the mass that's vibrating. That increases the rate at which we do work. That's also called power. More power makes it more intense. And so the sound just becomes louder. Again, force vibration is not something that I'd have on an exam or a quiz. But some of you that might be doing, like Sammy, AM and FM radio works on something called resonance, which is the next slide that I want to look at with you. So a very special kind of force vibration is when we get things to resonate. Natural frequency, the frequency at which an object vibrates naturally, often called its resonant frequency. Resonance is produced when we get an object to vibrate at its natural frequency. Resonance can be used to amplify, and it can also be used to transfer energy. And I want to show that with a recording with a set of pendulum. Now, we're not going to study the pendulum as an oscillator on an exam or a quiz, but I do want you to see how, in your case, Sammy, how we might tune something like a radio station. And so, since you're going to be doing the AM, FM radio stuff, this one would be a helpful analogy for you. You guys notice that on this set of pendulum, we have 4 different pendulums. 2 of them have the same length. Yeah. Those 2 that have the same length would have the same natural frequency of oscillation. Now, we didn't study that equation. It's the 1 over 2 pi squared of G over L. We didn't study that as an oscillation. If we had a full year class, we would do that up in that particular setup there. But this thing has a natural frequency of vibration. I'm going to set that into motion. Notice that when I set that one into motion, I have the other 3 that are vibrating somewhat erratically. I wouldn't say that they're picking up that vibration, but they are being forced into vibration. So I notice that they're sort of moving around a little bit, but they're not swinging like this one. So I'm going to stop there. I'm going to try this one. So Jonathan, can I have you move that one? This one has a low frequency of oscillation. I'm going to set that into motion. Again, I can get these things to pick up some of that vibration, but they're not resonating. And so sometimes it's pushing, sometimes it's pulling. I can get them sometimes to pick it up, but not completely. Now what I want to do is I want to set this one into vibration. So these 2 have the same natural frequency. So when I set this one into vibration, what I'd ask you to do is take a look at this one here. So I'm going to set that into vibration. And what you should notice is that the pendulum that has the same length is really picking up that oscillation. So its amplitude is sort of growing. And I think Jonathan can probably see that best. Is that one is now picking up that vibration pretty well. Sammy, if you're tuning your radio station and you want to tune to, let's see, 97 WGRD, you turn the dial here a little bit. What that does is it changes the resonant frequency that the electronics are going to pick up. If this is the broadcast, if this is WGRD broadcasting tower, you want your antenna to be able to pick that up. So you tune the frequency so that it has the same natural frequency as that, and it picks up that vibration. The others, you can sometimes hear static from a station that you're not tuned into, and that's because it can get a little bit of vibration but doesn't resonate at it. Okay? So that's the idea of resonance. So you'll see that when you get into your FM AM radio, that it's a lot of it's just about tuning through what's called resonance. Okay. Again, it's not going to be on your exam or your quiz, but Sammy's going to teach you more about that with AM, FM radios. I can tell. Could you guys, what I said here really seemed to resonate with you. Thank you. I'll be here all week. Okay, this will be on your exam and quizzes, right? So you want to make sure you have this set down. Nick, are you following along with me here? I'm not sure that you are. Get that notepad out. All right, your average ear can hear frequencies. Do you know what the audible frequency range is? The ability to hear sound between what frequencies?
8 and 5.
Thank you for that. Nice try. There's not. Wait, Sammy, did you say 8 and 5?
He said 20. Oh, 20.
Yes, he said 8 and 5.
8 and 5, as in like 8 in the morning to 5 p.m. 8 in the morning, 8 a.m. to 5 p.m. That's pretty clever.
8 Hertz, 5 Hertz.
8. What is it again, Wyatt?
20 to 100.
Nice try. It's 20 to 20,000 hertz, right? This is the audible frequency range. So your ear can hear sounds. The average ear can hear sounds between 20 and 20,000 hertz. Now I'm going to try this with my phone. I have an app on my phone that allows me to play a variety of frequencies. I want to check to see what your hearing sounds like. If you're able to hear these frequencies. Now, when you guys were younger, did you guys go through and do the hearing checks? They put headphones on. They say raise your right hand if you can hear something. I'm going to check that right now. And this data can go back to them and update those tests. So I'm going to check this with you. Okay, so I'm gonna go all the way down to about 400 hertz. You guys should be able to hear this pretty well. Okay, raise your hand if you can hear this. Are you ready? Can you guys hear it? Jan, can you hear it? Hear what? You can't hear something. All right. Now I'm gonna raise your frequency. Raise your hand if you can hear this. You can't hear that. It's about 1,000 hertz. So you're failing your hearing test. Right. I'm gonna go up to a little bit higher. That's about 3,000 hertz. Can you hear it?
Yeah.
Chase? Oh, there you go. Okay. It's about 8,000. Can you guys hear it?
Yeah. Unfortunately.
Okay, this is about 11,000. Keep your hand up if you can hear it. I'm going to check. I'm going to turn it off and turn it on. Raise your hand when you can hear it. Okay, good. Now I'm going to go up to a higher frequency. You guys can still hear that? I can't hear. This is gone for me. I can't hear this. This is about 12,300 hertz. Can you guys hear it? Raise your hand when you can hear it. Okay, this is about 15,000. Raise your hand if you can hear it. Lower your hand when you stop hearing it.
Seriously?
Ellie, you can't hear it?
No. I'm deaf.
Oh my gosh, all right. I'm going to go up to 16,000. We'll see if you can hear this. Hear it? Is it on?
Crazy.
Okay. I stopped hearing around 12,000, somewhere in that area. All right, I'm going to go up a little higher. Can you hear it? All right, I'm going to go up even higher. 20,000 is the highest that you're supposed to be able to hear. So what I'm going to do is I'm going to lower this down. As soon as you can hear it, I want you should not be able to hear this. Right now, this is about 20,000 hertz. Anyone hear it? Okay, it's on. Can you hear it? Okay, you tell me when it goes off.
No, I don't hear it.
Okay, so I'm going to lower it down. As soon as you hear it, raise your hand. Anyone feel it? You just can't hear it. Can you feel it? Feels like a cotton in your ear or something like that. Maybe a little bit of a headache. Can you hear it? Okay, that's about 18,000. Can I leave that on?
No.
You guys be okay? All right, I'm gonna stop that for a minute. You guys know that sometimes business owners that don't want young kids like yourselves sort of loitering around the areas, right? What they'll do is they'll play around their outside door, because you guys aren't like you're not like buying things, you're just sort of loitering. They'll play music like this. They'll play this. And this does not drive away. This does not drive away people like me, but it'll drive you guys away. Can you guys hear this?
No.
Yeah. So they will play that, and it's really annoying. Yeah, but they will do that because they don't want you guys just loitering, right? So there's a little application for it. All right. The ability to hear frequencies depends on age. As you get older, you're going to lose the ability to hear certain sounds. I've lost the ability to hear above around 12,000 hertz. Overexposure, true story. Dentists will sometimes lose the ability to hear the high-pitched whine of a drill. You have a question for me? Awesome. Thank you. All right, Connor, I will get that done. Get that graded. You got the essays? You chose the three things at the end paragraphs?
Yeah.
Okay, good. So dentist, that high pitch, raise your hand, you've ever had to have a filling done? The dentist will lose the ability to hear that after years of drilling out that cavity. Infrasonic is below 20 hertz. Ultrasonic is above 20,000. Now, I think someone in here has the ultrasound, and I don't remember who it is. Okay, so when you get to ultrasonic, it has to do with the size of the wavelength. And so most of the applications related to sound is based on the wavelength. The elephants are able to communicate in the infrasonic range. And the reason for that is they have a really large ear, and that comes from a really small frequency. So we would say that a small frequency, large wavelength. So for infrasonic, low frequency, large wavelength. Ultrasonic, this is going to be a shorter wavelength wave, and that's because it's got a higher frequency, so it's got a shorter wavelength. And then ultimately the ultrasonic, Reagan, if you're going to do ultrasound, we have to use a really, really high frequency above 20,000 hertz so that we get a very, very tiny wavelength to be able to go through, penetrate the skin, reflect off the baby or whatever it is that we're trying to see inside of that developing, inside that body. Right? So it has to do with the size of the wavelength. That wavelength becomes important. Pitch is strongly related to sound's frequency. The higher the frequency, the higher the pitch. So when we talk about pitch, it's related to the frequency. Okay, I don't want to do anything more with light. I'm going to save that for tomorrow. And so we only have a couple more days of content, and then we'll quiz you guys on Thursday, and then project start. Okay, so the last 20 minutes. Jonathan, I think you're done with that standing waves thing. But I have a little activity for you guys on sound waves and graphs.